name is Pierre Seifert. I'm from TU Berlin, and the title of my talk is Don't Worry About ORAN Security, ETSI has other headaches. So many will probably ask themselves, what the hell is this title about, right? Because we're all here for ORAN. But if you see where this is coming from, namely from a paper, Breaking the Quadratic Barrier, Quantum Cryptanalysis of Millinage, then you can imagine, it goes into the telco world. But, it's a long way to go there and the story, and therefore I will I will at least try to tell you this story, and I leave out many of those quantum fancy things because they are much more difficult to understand. So, the agenda of the talk is, first, I speak a little bit about ORAN security. Then I give you the telecommunication crypto one-on-one. That means the main road for crypto. And then a little bit why quantum computing is important for crypto. Also, most of us should know it. And then, the recent results on Millinage. And everybody should know, who's a little bit trained here in this security, should know that Millinage is that crypto backbone of the telco world. And then the implications for 6G, and the 6G man is Slavomir here in the room, right? And he knows this already a little bit. So, ORAN security. Well, before we start to speak about security, right, as a good teacher in university, we define what security is, because without a good definition, right, we cannot judge whether a system is secure or it's not secure, right? So that's very, very important. So there are two views of it, which I usually tell my students. The first view is the intersection view. A system is called secure if we have at least these three attributes. That means we have confidentiality, we have integrity, and we have availability. You both by yourself, you can all instantiate, those attributes, confidentiality, integrity, availability by yourself very clearly in a very formal way. But there's also another view, which is maybe more useful for the telco world. It says that computer security deals with the prevention and detection of unauthorized actions by users and others of a system. Actually, both definitions are from the Bible of computer security, from Bishop, right? It's not that I plugged them somewhere else and said, okay, yeah, I phrased the word as I like it. These are the standard definitions of security. But later, of course, if you speak about confidentiality, and that means encryption, you can have all kind of refined notions of what encryption should fulfill. But at least, these attributes. Okay, now we know what computer security is, at least for a broad understanding. Let's turn to this picture, right? So what we see from this picture is whenever we want to map confidentiality, integrity, availability in a clearly defined way to this complex piece of ORAN, it's, I would say, a complex and new field. We know that openness caused already in the Android phones a lot of trouble. So, but where to start to meet the definition? Proposals from you. Where should we start? Remember, just three things: confidentiality, integrity, availability. And I leave the choice to you where to start. And to prove that ORAN, fulfills at least these three things: confidentiality, integrity, availability. Sorry? Integrity. Okay, it's not bad. It's not bad. Actually, tomorrow I will tell about first integrity checks in this picture. So we developed some tools, how to do in an automatic way, do some simple integrity checks, on some small bullets. They work out of the box. You press the button and then give me some implementation in a black box fashion, and we will tell you whether they meet integrity or not. But today I leave it out, okay? And we have also a very small start, but tomorrow it's a more closed consortium, and therefore I tell this tomorrow because I also didn't want to tell it twice. Okay, but nevertheless, other people already start. In 2020, there was, this on LinkedIn, there was this paper pointing to this Ericsson research. And then, some in this room, they also know this nice paper from the BSI. And I called all this theoretical and claimish investigation, right? Because they all did the theoretical work, because they looked over the specifications and pointed out, oh, this might be weak, that might be weak, could be a problem, and that could be a problem, right? And if you go to this paper from the German security agency, you find some of those things. There were also two other papers. One from our friend co-authored, also from Heiko, was Adversarial Machine Learning Threat Analysis. So that gets even beyond, the simple things, confidentiality, integrity, and availability, because they look into machine learning-oriented things. And then there was also some paper by Slawomir here, which I don't want to comment. Maybe he can comment on it. It's also some attempt to investigate ORAN security. However, we all know that the real work on ORAN security is happening here, and the security focus group. All the other things so far, there were some blurred things about doing some theoretical work, and theoretical work might be nice, but not really practical. Okay, so that was, some pitch about the problem field, how difficult it is. What else can we say about ORAN security? We all know what the strongest weapon in security is. No matter, it is the strongest weapon. What is it? Every student learns this and everybody knows it, because if that breaks, you can go home. Hmm? Not? No trust. Ah, okay, somehow no trust. I got it. Okay, no trust. Okay. Trust is a wide word, right? But if we would break it down to mathematical terms, we could maybe at the end, agree that at least we would like to have confidentiality, integrity, all what you mentioned. Availability is another thing. But all we know is that cryptography is by far the most important thing. And if you go into things like cyber telecom, discussing, the problems of cryptography for the US and for all of us, you will see that cryptography is more than a weapon. It's the strongest weapon, because by this we can give our users, confidentiality in the encryption, confidentiality in the conversation. We can have, fulfilled correct accounting, because we can authenticate the user, and so on and so on. So, because it's the strongest weapon, so let's look what contemporary cryptography in 1G to 5G is worse. Because it's the strongest weapon, and let's see what it really is giving us. So therefore, the crypto one-on-one for telco security. We all know the crypto cellular world is defined by ETSI, and in this 3GPP standardization thing. And all these things better by myself, because I seldomly look into it, and only if I'm forced to look carefully into it, because they are terrible. And if you go into it, you see already here that it specifies the so-called millenage algorithm set, and there are these 7 functions. And these 7 functions are the absolute backbone of crypto in the telco world. As I said, the entire cryptography in our cellular world is based on those secret key algorithms, F1 up to F5, and there's also F1 star up to F5 star, and it's known as the AKA set, which stands for Authentication and Key Agreement. Everybody can imagine what this means. If you go into the specification, you see this terrible thing there, right? So it's, what cryptography in the secret key world looks like. That means XORs, rotates, constants, some blocks here, and and then all these things, sequence number, in order to provide integrity for broken packets and so on. So this is the 101. There's a known result because there are a lot of specialists working on this. It is known that these algorithms are provably secure by all means in the classical world. That means they cannot be distinguished from a pseudo-random number generator, they cannot be broken, this and that. You know, all kind of refinements in distinction what security for a secret key cipher or a pseudo-random number generator means. However, we all know 6G is around the corner, right? And it is envisioned in 6G that it cannot be broken even by quantum computers of arbitrary complexity. So that's the bold statement, right? Our friend, Fettweis and Holger Bocher, they wrote in the premium magazine of the ACM, they wrote this nice article, and they envision that 6G cannot be broken by quantum computers of arbitrary complexity. This way or that way, weakening a little bit this thing, I assume that ETSI will also agree within this year to some form of this statement, because 6G will be around for a long time and they have to do something and they have to investigate, make some thinking how to achieve this. But where are we now? Quantum computing. It started in '94 with Peter Shor, who came up with a fascinating paper which is entitled Algorithms for Quantum Computing, Discrete Logarithms and Factoring, a milestone article. This was, to a certain extent, a bomb in the crypto landscape because nobody had ever thought to break the contemporary cryptography based on factoring and discrete logarithm. This way or that way, discrete log and factoring are the prominent problems for today's public key cryptography. Remember, our telco word is secret key cryptography, right? Okay, so, but at that time, people said, oh, boring, quantum computers are not existing. Second, it will not work because you cannot build Schrödinger's cat. We all know this, right? Because at that time, people said, forget about it, it's not working because you need quantum error correcting codes, and that by first definition, there can be no quantum error correcting code, principled by the no cloning theorem. But all, was overcome after some time, and the story went on. But let me explain why it's so important, because it broke the RSA scheme, which was invented, I think, somewhere in the mid-'70s by those three famous men, Ron Rivest, Adi Shamir, and Edelman. And this protects our entire digital life. Whether you use elliptic curves or RSA, it doesn't matter. They were the first, and all this crypto is used wherever you have, to trade secrets, or you have to trade money or whatever. We all know blockchain at the end of the day, and it uses public key cryptography. So what is the main key takeaway from Shor's algorithm? The main key takeaway from Shor's algorithm is that if you consider the compute resources to break RSA, whether it's RSA or elliptic curve crypto or public key crypto, the logarithm of the compute resources, it goes on the linear red line, whereas the quantum algorithm goes logarithmic. You see, the problem size is increasing. If you take the logarithm away, you can imagine that the traditional algorithm needs exponential resources, where the quantum algorithm needs only a polynomial number of resources. That was theoretically, in the age of a quantum computer, the end, or is the end. But now let's look, where is the reality of quantum computers, right? We need to know that. What was the timeline? In '99, Michele Mosca, a prominent guy from this field said maybe 20 bits in 20 years. Okay, 2015, NIST said a 7 chance of breaking RFA 2K by 2026 and a half chance by 2031. And in 99, in sunny California, see that they live in sunny California, 2 graduate students broke on a machine, terrible large and very expensive. They factored 15. And they showed on a quantum computer that you get the result 3 times 5. And the machine, needed 11.7 Tesla, something nice, right? Or the physicists can tell you how much energy you need to have this field, right? Heiko? Sorry? It's a lot, okay? And then, therefore, in 99, people said, okay, yeah, if you want to have, this required 4 bits, okay? For 4 bits, you required 11 Tesla. So people said then, okay, yeah, if you have, let's say 8 bits, you need more Tesla and more. Today we have many Teslas here in Brandenburg, right? Okay. So this is the story, right? And the projection. So are there implications for ETSI? The algorithm set is called millinage, or AKA. Remember, the entire cryptography is based on the secret key algorithm. So, is ETSI lucky? Because by no means this Shor algorithm will work on the millinage algorithm. Never, ever. This was clear to the people. But, we don't want to speculate about lucky and happiness. We want to have, the hard research question. Are existing, small, and noisy quantum computers a threat for ETSI? And all these 3 things which you see here, right, 49 bits, 72 bits, 50 qubits, they are all, no doubt, small, noisy, but existing. So, but what is small? Small is relative. The timeline of IBM is, they delivered this year already a 127 machine, and by the end of this year, they will have 433 bits. So you see, by the end of this year, and I believe them, they will have 433 qubits. A bit noisy this way or that way, but you see the timeline progresses with the number of qubits. I would say, until here, all is okay for our usage. But after that, it gets a bit more blurry, but we will have soon around 1,000 qubits by the end of next year. So, you can imagine what the question is, right? What is now the status of millinage in the quantum world? So, what you have to do is, you have to take these ciphers, plug for EK, the advanced encryption standard in it, and do a quantum crypt analysis. Good luck. Takes some time until you understand all this, how Shor works, many books, many lectures. I have a student, Vincent, damn brilliant. He came to me and said, hey, Jean-Pierre, we should go after millinage with quantum. I said, Vincent, come on. Many people looked at it, nothing will come out. I said, this argument, that argument, and I wasn't convinced. And then he explained, yeah, you could use this structure and that structure, and then we looked into it. First proposal from him, many errors, but we could fix it at the end because some constant there is a 0, and exploiting that a constant is 0, and there is no rotation, for F2 and F5 does the job finally. So the outcome is this monster table. I will explain you this monster table. This monster table shows you that the best known classical attacks against any of those 7 algorithms is, of course, 2 to the key length. So this is the key length of millinage, and this is, of course, 128. So Therefore, to make it look better, we have, this abstract form, but actually it's Internet by 128. Also, mathematically it does not make sense because it's big O of some constant. But, it looks better if K would be some variable, but forget about this. So there's a trivial algorithm, Grover's attack, which is usually cited in this quantum world and telco, which has a complexity of square root of this. You see, 2 to the K half. And therefore, the argument was always, okay, don't worry about quantum computers in the ETSI world because just double the key length, then you can compensate for it. That was the argument. And therefore, the paper is also called Breaking the Quadratic Barrier, because the question was, can you do better? And yes, we can do better, but it's complex to explain. Because what we have here is, we have two different models, namely the Q1 model and the Q2 model. And depending, it's of course clear, if you have the strongest model, you get the best results in complexity, breaking, for instance, or coming up with an extensional forgery for F1. And extensional forgeries for F1, whatever this is, were excluded to be allowed by ETSI, and therefore it is also not existential forgery, in the classical world. However, in the quantum world, we have a complexity of the message length to the cube. Or if we have related key attacks, we can break it also in the power of 3 in the key length. So these are polynomial attacks. If we go to another model, you see that we can divide the key length by 3. And though you can go through the table by yourself, the paper will be uploaded within the next days and you can decode it. However, the problem is this new model Q2. In the crypto world, it's already done. The crypto world says this is a new model to do cryptography. Some people, if you speak with them, they say, okay, it's difficult to conceive this Q2 model, whatever this Q2 model is. However, nowadays, the first theoretical paper started to implement the Q2 model via the Q1 model. These are fairly theoretic, but you see, also the quantum computer was for many years fairly theoretic. So I wouldn't underestimate that sooner or later this Q2 model is possible. But even only with this Q1 model here, this breaks the quadratic barrier. I know it was fast on this question on this table from the experts. Sorry? Well, it depends where you go. 128 to the power of 3. Sorry? The last one, well, it's not a huge number. It's 128 divided by 3. Yeah, it's in the exponent, but it's a completely different, it's a classical model, whereas in this more advanced model, you have polynomial time index. And people also, they demanded in the ETSI standard that the complexity is under all circumstances 2 to the k, and not 2 to the k by 2 or 2 to the k by 3. Okay? The standard demands it must be secure relative to this number, 2 to the k steps, and not divided by 2 and by far not divided by 3. So why do you think they have abandoned SHA-1, Slavomir? Yeah, it's a huge number, but 2 to the 60 nowadays, it's the end. Because 2 to the 60 can be done. Nobody in a standard would accept a standard with a complexity of 2 to the 60. Okay? And dividing 128 by 3, it's beyond 60 as exponent. But we did this only because for completeness, because we wanted to have the table complete, but the main result is here. Okay, but now comes the summary already. And the summary contains something more devastating in a nice, gentle form, but somebody as Slavomir can probably nicely decode it. So, now the implications for 6G. First thing is, our attacks require only a very small number of qubits in total, probably 256 plus epsilon. Number of qubits to break millinage. All 7 algorithms, F1 up to F5, and even with the star. You see, it's different to RSA, because for RSA, you need thousands of qubits to break, 2K RSA. Here, first estimate is 256 plus some epsilon. Next point is, so doubling the key size is not a recommendation, because doubling the key size was shown not to hold, because you will always find, some hole in there, or you can exploit some algebraic structure to circumvent this doubling of the key size. Let me go back and explain you, the disaster. So disaster is actually, here is the AES in it, but all these nice structures, rotation, adding a constant here, adding OPC, which is the operator codes, and there's an encrypted operator code, all these nice things, these nice, here you XOR something, there you XOR something, there you rotate, and there you have all these things. Also, EK is completely secure. Just adding, all this mathematical structure, which was very good in the classical world, breaks all these algorithms in the quantum world, because you can construct so-called periods and exploit those periods to come up with polynomial time attacks. That means we have to understand in the future how such a structure must be changed and avoided not to allow periods. You see, this box and this box is the same. It's okay. It's secure under the quantum computer. But, adding more structures, which are very useful for our world, is a killing argument. So, we were here. Doubling the key size doesn't hold. That means we gave strong evidence against choosing millinage as a cryptographic cipher, underpinning the security of quantum-resistant telecommunication networks. So millinage will not and should not, go to 6G. The research question is really, what security guarantees and what kind of quantum adversarial models should be used in the quantum security considerations for cellular 6G? As the classical cryptographer developed many models for security, even in the documents from ETSI, what they consider secure and what kind of attacks, forgery attacks, this attack and that attack, should be not possible. It must also be researched now. It's completely unclear what is the right model, what is the right security notion. It's open. The big question is really, is ETSI staying with secret key crypto? I have no idea whether this is possible at all, or will they change to public key crypto with all the problems. So far, the public key world is better researched against the quantum computer, because the secret key world under the quantum computer is not understood. And since almost 10 years, we understand what a crypto algorithm in the public key world, how it has to look like to withstand quantum computers. But the secret key world, it's very fragile and not understood. Lots of research years ahead of us, Slavomir. And now, I give you the chance for questions because I'm ready.